Hi everybody, welcome to section 1.2, which is all about graphs of equations. So in this section we're going to review how to graph an equation. There are many different ways, we'll talk about a few, but we'll be doing this all semester. And then I'll also remind you of just some basic properties of simple polynomials. Okay, so we've been looking so far at algebraic expressions and simplifying them. In the last section, 1.1, we reviewed the Cartesian plane and coordinates and plotting points. But when you have an algebraic equation, like something like this, y equals 4 minus x squared, what you can do is make a picture of this equation. And the picture consists of all points x comma y that satisfy this relationship. Okay, so that's what we call a graph. The graph of an equation is a really cool picture of the solution set of all points that make the equation true. One way to graph an equation is to plot a bunch of points. This is a tedious way, but it does work. So let's review how to do that. Okay, so let's graph y equals 4 minus x squared. You should have a sense of we'll talk about this in a little bit, but the general shape of what this looks like, you should remember that. So this is a quadratic. We have a 2 in the exponent, the highest degree here. And so those either look like this or they look like this. These are called parabolas. And depending on the sign in front of the x squared, so here it's a negative x squared, that determines which direction the parabola opens or is curving. Okay, so when we have a negative in front of the x squared, that's going to be like this. A positive coefficient in front of the x squared would look like this. Okay, so let's plot this by plotting points. So you can basically pick any points you want when you're plotting something in this way, but a good idea to organize your work might be to make a chart. And we're basically just going to choose a bunch of different x values, and we're going to figure out what the y values are that go with them. So it depends on where your axis of symmetry is, if you remember what that means, and what your vertex is and stuff, to get a nice picture centered around important features of the parabola. But if you're not sure, I mean, a way to just go about plotting something might be just to start at 0 and go out in both directions a few numbers. So let's just go out 3 from 0 in both directions. So to find the corresponding y value, we don't have to guess, there's a rule for that. So it says that y equals 4 minus x squared. So whatever x value we have, we're going to just plug that in for x here, and we'll find the y value that goes with it. Okay, so 4 minus parentheses negative 3 squared. Okay, negative 3 squared is 9, so this will be 4 minus 9, and that gives us negative 5. Okay, so this is telling us now that we have a coordinate of x, which is negative 3, and y, which is negative 5, that lies on the graph of our equation. Okay, well, we'll keep on going. We'll plug in negative 2. Okay, 2 squared is 4, so that's 4 minus 4, and so that's 0. And so the coordinate pair that's on our graph, the second coordinate, is negative 2 comma 0. Okay, we'll keep on going, plug in negative 1. Negative 1 squared is positive 1, and 4 minus positive 1 is 3. And so here is another coordinate, negative 1 comma 3. Okay, here we're going to plug in 0 in for x. That'll just be 4. Okay, so then we have oops, wrote that backwards. X is 0 and y is 4, so 0 comma 4. Plugging in 1. Okay, now we're squaring the 1 first and then subtracting it, so this will still be 4 minus 1. So that'll be 3. So that's x equals 1, y equals 3. Okay, then we've got 4 minus 2 squared. Okay, we square the 2 first, so that'll be 4. So this will be 4 minus 4, and that's 0. You can see the symmetry maybe that's coming up here. And then 3, 4 minus 3 squared, that'll be 4 minus 9, which is -5. And so there's another coordinate that lies on the graph of our equation. So all we're going to do is plot these on the Cartesian plane. So take a look, we have x values that are between -3 and 3, and our y values go from, well, a -5 to 4. So you can just take a look at that to kind of see what your axes should look like. So I want to basically have a nice range on both positive and negative x and y. Make sure we label your axes. Okay, we've got out to 3 on the x-axis. Kind of makes it go out a little more than that, just to have it give you some space. But you want to go at least to -3 and 3. Maybe it looks something like this. And then our y goes from -5 to 4. So I'll just go out to 5 on both directions. Okay, so now we can go ahead and plot the points that we have. So we can just go one at a time. So we've got -3, -5. All right, so that point lives right here. There's -3, -5. Then we've got -2, 0. So that point lives right here. Okay, that's on the x-axis with a y value of 0. -1, 3. Okay, that's going -1 up 3. So that's right here. Okay, then we've got 0, 4. So that's 0 on the x-axis, then up 4. So that lives on the y-axis. Okay, then we've got 1, 3 right here. So that's 1, 1, 2, 3. So that's point lives right there. Then we have the point 2, 0. Okay, so that's out 2 on the x-axis, 0 on the y direction, and then 3, -5. And so that is about here. All right, so we can see that we have a downward facing parabola. Now we could have plugged in, we plugged in the points here that are on the nice whole numbers. We could have plugged in any point that lives between these. And what happens is that you get this nice, like we would just get a bunch of points that would form this nice shape. Okay, so it's not, a graph is made up of infinite number of points. We can plug in some and then use our knowledge of what the shape of these things should look like to kind of piece it together. And so there he is. There's the graph of y equals 4 minus x squared. Okay, this is a very tedious way of plotting, of graphing, an equation. So we'll talk about a second way, but before we do that, I just want to review with you what the exponents can kind of tell you when you're looking at an equation. Okay, so they can give you a lot of information. Okay, so for simple polynomial equations, so let's just talk about what that means for simple polynomial equations. Okay, that means a polynomial is powers of x that are added and subtracted together, and maybe they have numbers multiplied by them. So as opposed to things like trigonometric functions or logarithmic functions or exponential functions, okay, polynomials are really nice. They just have x raised to different powers. Okay, but the largest exponent on x and y tell you the largest number of times that the graph can intersect certain axes. Okay, so the largest exponent on x would tell you the largest number of intersections the graph can have on the x-axis. The largest exponent on y will tell you the largest number of intersections the graph can have on the y-axis. Okay, so this is true for, I'll just review up to like a third degree, but this is true up to however many, the 1,000th degree, 2,000th degree, like all the way up. So for linear equations, you should be familiar with the format of the algebraic form and the graph, and we should be able to put them together. Okay, so linear equations, we might remember that this is y equals mx plus b. And we will review linear equations in depth in the next section, 1.3. Okay, so the exponents that we have here, we've got an exponent on the y of 1, and we've got an exponent on the x of 1. And so that tells us that the maximum number of times that the graph can cross each of these axes is once. And here's just an example of one line. Okay, of course, lines can have different slope and be moved around, but they're not going to cross the x-axis more than once. And they're not going to cross the y-axis more than once, right? There's the largest number of times that you can have. And you can just think like, all right, if I have a line with negative slope, like maybe it's even down here, right? It's going to cross the x-axis and y-axis here. Lines that are horizontal, again, we'll review this in the next section. They look like this. And you might say, well, that crosses the y-axis here, but it doesn't cross the x-axis. And that's okay, because this is saying that the exponent on x and y is the largest number of intersections that is possible. Okay, so what this is saying that a line will never cross the xy axis more than once. It's not going to turn around and cross the x-axis again, because then it will no longer be a line. All right, with quadratics, we have this kind of format. We write it as y equals ax squared plus bx plus c. Right, here we have the exponent on the y is 1, and the highest degree on the x is 2. So this means that the quadratics will cross the y-axis no more than 1 time, and they will cross the x-axis no more than 2 times. Right, here's an example, and we just saw an example of this, where the parabola or the quadratic looks like this. Quadratic is the name when it's written in an algebraic way. Parabola is the name for the shape or the graph, but they go together. Okay, so the y-axis gets crossed once, and the x-axis gets crossed twice. But you could have a parabola or a quadratic that looks like this, where it just kind of bounces off the x-axis once. And it could be the other way too, like, so it could go down like that, it could be moved around. This is just one example. So here we have one intersection on the y-axis, and here we just have, it's weird to think of this as an intersection because it doesn't cross or go through, it just touches it just barely at one point and then just turns around again right at that vertex. All right, so here we have one intersection on the x-axis, and that's okay because 1 is less than the highest degree of 2. We could even have 0 intersections on the x-axis. So you could have one that looks like this, a parabola that will never cross the x-axis. Here we just have an intersection on the y-axis. And again, that's okay. What this is saying when you have degree 2 is that the graph is not going to turn around again and cross the x-axis for a third time. All right, however, cubics will. Right? Cubics, we add another degree. So here's how we would represent a general form of a cubic, where we have the degree of 3 on the x. Here we still have degree 1 on on y, and then here our largest degree on x is 3. There are a lot of ways that cubics can look. I'll just sketch one for you. Here is a general shape. So they kind of can be sort of like two parabolas kind of glued together, maybe going in opposite directions. But you could have them shaped differently, like it could the bumps could be in different places. So here's how you could have different ways that the axes can be crossed. They could even be flipped around, maybe like this, or like this. We'd have 3 intersections again. Or here you could have 2 intersections on the x-axis. Okay, but the point is you're not going to have 4. So here's just an example where we have 3 intersections on the x-axis, 1 on the y. Okay, so 3, 2, or 1 intersections would be valid for a cubic. All right, here's the only example I will talk to you about with an exponent on the y that is not 1. Okay, so the simplest equation that you can get with that really is a circle. And I'm going to draw 2 different kinds that we can have. So let me just scroll down here a little bit. X squared plus y squared equals r squared. Okay, this is an equation of a circle whose center is at the origin. In other words, 0, 0. So here we have the exponent is on the x is 2, and the exponent on the y is 2. Okay, so and we know that the shape of the circle is going to look like it's centered at the origin. The r is the radius. Just for a little bit of a refresher on that. So the r here is the distance from the center out to any point on the circle. Any point at all, here, 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 all these points are the same distance from the center. So that's a number. Okay, and so here we have the y intersections is 2, and the x intersections on the x-axis is also 2. Okay, but no more than that, no more intersections than 2. You can move a circle around to have a center at a different point. So if we just say, here's a circle where the center has a different coordinate. So let's say that the center here will be not 0, 0, but in general, we usually use the letters h and k. So we'll say h, k. The algebraic structure for that looks like x minus h squared plus parentheses y minus k squared equals r squared. Looks kind of crazy, but what happens is just the x coordinate of the center gets subtracted from x. These will be numbers. Okay, the y coordinate of the center gets subtracted from y in the equation. Again, these will be numbers. And what that does is it shifts the circle around left and right and up and down. Okay, now here we don't have any, the highest degree on x would be 2. The highest degree on y would be 2 as well. But here we don't have any intersections on either axis. That's okay, right? There's just not going to be 3. We could have 1 on each by maybe having a kind of bounce off of the axes, and that would be fine. All right, now there are also like quartics, which is to the 4th degree. Instead of 3rd here, we have quintics, which is 5th degree. What happens is you just keep adding in a bump. So this would look like a quartic, like a W or an M, depending on if it's positive or negative in front of the leading term. Quintics, 5th degree, just adds another bump like that, so it looks something like this. Or if they're flipped around, it looks something like this. Okay, so that's the general idea of polynomials. Okay, so we're going to delve a little bit deeper into this idea of intercepts and finding them algebraically. So we just kind of gave you a brief overview of how many that you might have given any kind of equation. So let's look at how we find these algebraically. Okay, so intercepts, we've got 2 different kinds, like we just said, x and y. And to find them, the process is similar, but slightly different. So I'm just going to draw a nice little picture of a simple line here to help illustrate. So let's label. Here's the y-axis, here's the x-axis, right? Here's the x-intercept. and here's the y-intercept. Okay, so just in words, the y-intercept, of course, is where the graph crosses the y-axis. It's a purely graphical thing. But again, we're going to look at now how to find it algebraically. Okay, so the y-intercept is where the graph crosses the y-axis. Similarly, the x-intercept, right? This is, of course, where the graph crosses the x-axis. Okay, so looking at each of these, they're coordinates on the curve, and there's certain features about any y-intercept and any x-intercept. So if we just look at the y-intercept for a moment right here, its coordinates, well, we don't know what the y value is because it could be anywhere along here, even negative. But the common thing about any y-intercept is that it lies on the y-axis, and so the x-coordinate for any y-intercept will be 0. I don't know what the y-coordinate is, so I don't know, we'll just call that like b. Okay, so 0, comma b is the kind of format that y-intercepts have. So to find the y-intercept, what you want to do is set y equal to 0. If you have an equation, oops, that's not right at all, sorry. Set x equal to 0. Okay, x is 0, we want to find y. So we're going to set x equal to 0 and solve for y. Okay, and then similarly for the x-intercept, okay, right here, we don't know where the graph is going to cross the x-axis. We're looking for the x value, right? It could be here, it could be over here, it could be here, it could be way over here, and there could be more than one. But the thing about the x-intercepts is that the y value is always 0. Okay, so let's call this like a here. This will be a comma 0. So to find any x-intercepts, what you're going to do is set the y value to 0 and solve for x. Okay, so let's look at example number 1, which is 2y minus 3x equals 6, and we're going to find the x and y intercepts. So this, I hope you look at this and you can tell that because we have an exponent and on the x and y of 1, that this is going to be a line if we were to graph it. And so we'll have at most one intercept for each x and y. Okay, so let's look at, doesn't matter which order you do them in, let's do the y-intercept first. It tends to be the easiest, so I like to start there. So let's see, we're going to find the y-intercept first. Okay, so to find that, we're going to set x equal to 0. Okay, so we're going to plug in a 0 for, oops, a 0 for x into your equation. That leaves you with just a y to solve for. Okay, so 3 times 0 is 0, so it's just 2y equals 6. And so we'll divide by 2 on both sides, and that gives us y equals 3. We want to put this as a coordinate, so here we have the x-coordinate of 0 and the y-coordinate of 3. And so the y-intercept would be 0, comma 3. All right, now our x-intercept, we're just going to do the opposite. Oops, I think I was using, be consistent here. I think I was using green for that. So let's see, our x-intercept, we're going to set y equal to 0 and solve for x. Okay, so we plug in a 0 for y into our original equation here. So we'll have 2 times y minus 3x is equal to 6. 2 times 0 is 0, so that leaves us with negative 3x equals 6. We'll divide by negative 3, and that gives us negative 2. And so the coordinate of our x-intercept would be negative 2, comma 0. Now this is another way that you can graph equations of lines. is by finding the intercepts. It's pretty easy to do that, more so than finding a bunch of points and connecting them. So just as a brief reminder of that, let's sketch this line. Whoa, that's not what okay, let's see. Set up your axes. I need to basically go out to, I don't know, I'll just make it out to 4 everywhere. Okay, so our x-intercept is -2, 0, so that's right here. Our y-intercept is 0, 3, so that's right here. And so if we connect them together, there's the graph of that line. All right, example number 2 is now a quadratic. It's got a degree of 2. So that means that we're going to find at most 1 y-intercept and either 2, 1, or 0 x-intercepts algebraically. Okay, I like to start again with the y-intercept because I think it's easier and makes me feel good to do something a little easier first and get warmed up for the harder stuff. So we're going to set x equal to 0. So let's see, we'll have 2y equals 0 squared minus 2 times 0 minus 3. So it leaves us with 2y equals -3, and we'll solve for y, and that gives us y equals -3 halves. All right, so that means our y-intercept is going to be 0, -3 halves. Okay, now our x-intercept. Here we're going to set y equal to 0 and solve for x. So plugging a 0 in for y, we'll put a 0 in on the left-hand side, times 2. And of course, that's 0 on the left. And we're left with solving this. Now in the previous example, we didn't have a squared term, so solving for x and y was pretty straightforward. But here we are trying to solve a quadratic, right? We have x's in multiple spots, different powers. The highest one is 2 here. And we're trying to solve this for x, and it's set equal to 0. The only tool, I guess you have 2 tools in order to solve something like this. One of them is the quadratic formula, but no one wants to use that unless you absolutely have to. So you always want to try to factor first. Okay, if you were thinking about bringing this over to here and maybe trying to solve for x, that is not going to ever help you. So you always want to get 0 alone on one side of the equation and then factor. Okay, so this is a quadratic with a 1 in front of the x squared. So if it's going to factor, it's going to look like this. And we're going to need 2 numbers that multiply to -3 and write this last value here and add up to -2. And I think that numbers like that exist, like -3 and +1. So now here we have 2 things multiplied. And the only way that you can multiply 2 things together and get 0 out is if one of those 2 things is equal to 0. All right, so then that means we consider each of the factors. Okay, so this equals 0 when x equals 3. And this factor is equal to 0 when x is -1. Okay, and so that will give us 2 x-intercepts. 2 x-intercepts, right? And that makes sense because we had a quadratic here. At least we didn't get 3, that would be bad. All right, so you've got 3, 0, and we have -1, 0. So those are our 2 x-intercepts. Now you could use these points to help you plot the parabola or graph the parabola. It's generally not so easy to plot a parabola with or a quadratic with the intercepts because you don't know, that doesn't necessarily give you the vertex like this point here or this point here. So it's hard to know exactly what the shape is. So I wouldn't recommend using this way to plot or graph parabolas or quadratics. we're not really going to need to necessarily do that too much, so we'll just leave it like this. All right, lastly, we have this thing here, which is not a parabola. It is actually a fraction, right? And when you have this situation where you've got a polynomial up top and a polynomial in the bottom, this is called a rational equation or a rational function. Okay, these have some issues. Right? When the denominator is equal to 0, their domain gets weird. Right here, you can plug in anything at all. Here, you can plug in anything at all for x. But here, there's a restriction on the x. Okay, x can't be equal to 2. Just a little refresher about that. So it won't matter too much, but we can just say domain is all real numbers except 2. So negative infinity to 2 and 2 to infinity. Okay, so that doesn't really matter when we're finding the y-intercept. So let's go ahead and do that. Then we're going to set x equal to 0. Okay, so that'll give us negative 4 over negative 2. And so that is positive 2. So the coordinate for our y-intercept will be 0, 2. Okay, x-intercept time. Here we're going to set y equal to 0. This one's a little bit trickier because here we have a fraction and we're figuring out when it is equal to 0. So you might have several different things that come to mind. One of them might be that, oh, you can like kind of remember cross multiplying. This is really like over 1. And so if we multiply across here to get rid of the denominator on the right hand side, we're going to just get 0 is equal to x squared minus 4. That's a little bit of a problem. It was actually a big problem because that's going to, well, you'll see why. I'll show you by way of telling you how to actually do this and we'll see why. So I would say in this case, let's factor the numerator. So this is a really nice difference of 2 squares. I love factoring them. They're so much fun. So easy to spot and easy to factor. Now the numerator will be 0 when x is negative 2 and x is positive 2. And that is going to maybe give us 0 because whenever you have 0 on the top and you have a number on the bottom, then this is equal to 0. However, there's a problem when x equals 2 because that's not in the domain of the function or the equation. So when you're trying to solve for the x-intercept, you actually can cancel these out here. We'll talk about this a little later, but this is what we have as a whole at x equals positive 2. Okay, now we have 0 equals x plus 2, and that is different than what you would get if we were talking about before, if you cross multiplied and got rid of this before factoring. Okay, because then you would end up with having both solutions of negative 2 and positive 2 for x. Okay, so when we solve this for x here, we're going to get negative 2 is equal to x. So that's our only x-intercept. So the way that we write that would be negative 2, 0. Okay, like I said, we'll get into a little more about like holes and things in graphs. If you don't remember that, we'll talk about that in section 1.5. But for now, this is kind of the only thing we need to worry about that might be a little tricky with finding intercepts. Okay, one last topic in this section 1.2, and that is about points of intersection. So points of intersection, this is exactly what it sounds like. It is where two graphs meet each other. Or cross. Or go through the same point. The same point on the graph, so it's going to be a point that's like x comma y. So they have the same coordinate at that point. Okay, so when we're trying to find the intercepts, when we're trying to find the points of intersection, since they have the same x and y, what we are going to do is equate them. So we're going to say, okay, well, if y equals this and y is equal to this, if they have the same y value at the point where they intersect, then this and this have to be equal to each other. And then we'll be able to solve for x. So we're going to equate equations and solve for x. Okay, so let's find where y equals 4 minus x squared and y equals 2x minus 1 intersect. Okay, so we're going to equate them. So we'll say 4 minus x squared is equal to 2x minus 1. So step 1 is just setting those equal to each other, just writing that down. And now we have to figure out how to solve this for x. So looking at it, it's a quadratic because we have an x squared term here. So there's no way for us to just isolate x anywhere. We're going to need to eventually factor, or perhaps use the quadratic formula if it's not factorable. So you have some options here, but we want to get 0 on one side of the equation in order to do either of those things. You have options about which side to get 0 on. I would always recommend trying to get a positive number in front of the thing with the highest degree. So I would say let's bring all of this stuff over to the other side so that we'll have a positive in front of the x squared. Okay, so let's do plus x squared minus 4. Let's do plus x squared minus 4. So that cancels on the left and gives us 0. On the right, I'm going to write this as an x squared first. Then we have plus 2x. And negative 1 minus 4 is minus 5, or negative 5. All right, let's try to factor this. So we need two numbers that will multiply to negative 5 and add up to positive 2. Thinking about that, I don't believe that's possible, right? 5 is only 5 times 1, and that's not going to add up to 2 no matter what sign we put on 5 and 1. Okay, that's all right. That just means that we have to use a quadratic formula. It's not factorable. Use quadratic formula. So let us review what the quadratic formula is. Okay, it solves something that is in this format for x. So it gives us this formula: x equals negative b plus or minus square root of b squared minus 4ac all over 2a, where the a, the b, and the c are the coefficients in the quadratic that we have here. Okay, so a is 1, b is positive 2, and c will be negative 5. So go ahead and take a sec to pause this and write down what you think you'll get when you solve for x here. Okay, negative b is minus 2. Okay, b squared is 2 squared. A is 1 and c is negative 5. Then we've got over 2a, which is 1. All right, simplifying, we have negative 2 plus or minus 4 plus 20 all over 2. And then it's negative 2 plus or minus 24 all over 2. Now you could get, I'm just going to move this over here to have a little more room. You could get a decimal approximation for this, but we can also simplify this in a more exact way. 24 is not a perfect square, but it does have a perfect square hiding inside of it. Okay, 24 is 4 times 6. And the reason that I'm thinking about doing this is because, well, I see that there's a 2 here and a 2 here, and it'd be nice if we could maybe cancel these out. But remember that that's a hugely bad mistake to make in math. It's a fatal mistake, so we can't cancel these out because you're completely ignoring that this root 24 is also being divided by the 2. So what we'll have to do is see if we can factor out a 2 from the numerator, because then we can cancel the 2. So I'm looking to see if there will be one, and I think there is, because right, this 4 can now come outside of the root as a 2. Now 6 is 2 times 3, but neither of those are perfect squares, so there's no point in, looking further for that. Okay, now we can factor out a 2 from the numerator. And here is the lovely time where we actually can cancel these. Okay, we're multiplying by 2, and then we're dividing by 2. And so those will actually cancel out. And so what we are left with here is -1. Oops, and I dropped the plus or minus here, sorry. So -1 plus or minus radical of 6. Now this isn't one number, so it's always best to split this up into the actual value. So we're going to get -1 plus radical 6, and then also -1 minus radical 6. And so those are your two, at least the x values, of the intersection points. All right, so what we have going on here, this is just a really rough sketch of the situation. You can just use the shapes that we know. So we actually plotted this already. 4 minus x squared. That's a parabola that looks like this. Okay, so this is y equals 4 minus x squared. Okay, 2x minus 1. This is a line or a linear equation. We'll go into this in more detail of a review in the next section, but it's got a y-intercept of -1 and a slope of 2. All right, so that just kind of, I don't know, just looks something like this. All right, I don't have a scale here. I'm just trying to give you a sense of the shapes and everything. So the scale isn't too important. Okay, so what we found, our points of intersection are here and here. We only have the x values, so you could say here, okay, this would be the positive one, so that's probably this number here. Okay, -1 plus radical 6. And then the x value here, right here, this would be -1 minus radical 6. And that is it. So if we wanted to find the y values of these points, I'm not going to have us do it in this particular example. But if we wanted to find the y values, which I believe your second homework assignment does ask you, right? So this would have the y value, this point here, right? The y value would be here. This point here would have the y value here. All we would need to do is plug in each of these x values into here, right, to find the y, or here to find the y. Okay, it doesn't matter which. Why is that? Right, well, the y values are the same, no matter which curve you're on, at least at the points where they intersect. So that's how you could do that. All right, let's look at one more example here of finding points of intersection. Here we have a cubic function, or a cubic equation, and here we also have a quadratic, and we're seeing where they intersect. Okay, so step 1 is setting them equal to each other. So just write that down, just equate them. And I'm a little intimidated by all of the x's here after I've written this. Well, let's just keep going and see what happens. So, right, factoring will be the best thing that we can do to solve this for x. And in order to get there, we're going to want to get 0 on one side. Okay, now which side? Well, I don't know. I've got a cubic here. It's already positive. It's just a little easier to work with when you have your leading term or your highest degree with a positive exponent. So I'm going to leave all of this stuff on the left, and I'm going to bring everything else over to the right. So all that stuff on the right is going to cancel. I'm going to line up the plus 2x squared and the minus 13x and the plus 5 on the left with the like terms that we can combine. Okay, negative 3x squared plus 2x squared is negative 1x squared. 1x minus 13x is negative 12x. And then negative 5 plus 5 is 0. So here we are. That's looking a lot better. Okay, now we have, well, we have a cubic, but so there's no real way to, like, I don't know, reverse FOIL this yet or anything, but I think looking here, it's easy to see that we have a GCF. Okay, so we've got a factor using any of the methods that we know already. Now let's factor out a GCF here of an x. Okay, now here we've got x squared minus x minus 12. Now that might be factorable, so let's see. Let's cross our fingers and hope we don't have to use the quadratic formula again. So we need two numbers that multiply to negative 12 and add up to negative 1. Oh, I think I found some negative 4 and positive 3. I think those work. Okay, great. So now we have three things on the left side, three factors. Okay, x minus 4, and x minus 3. And so this product will be 0 when one of the three factors is 0. So when the first factor here, this will give us x equals 0. The second factor here, if we set that equal to 0, we get x equals 4. And the third factor here, if we set that equal to 0, we get x equals negative 3. Okay, so these are our three x values of the intersection points. Now, if we wanted to, we could find the y values as well. So here might be a good way to practice this. So let's find the coordinates. Okay, so finding the coordinates of the points of intersection. Okay, this is going to be x comma y. So let's do these separately. If we have the x value of 0, let's see, we're going to plug it into, well, we've got two choices. Remember, the y values are the same at these three x values. So either one you want to choose is fine. I think this one's easier because we only have, three terms to sort of deal with as opposed to 4. So I'm just going to go with this one here. Okay, so again, here's what we're doing. We're plugging in to either equation. Okay, so we've got x equals 0. So let's see. Negative 2 times 0 squared plus 13 times 0 minus 5. Well, that's negative 5. All right, so the intersection coordinate would be x equals 0, y equals negative 5. There's one of them. Okay, x equals 4. Okay, negative 2 times 4 squared plus 13 times 4 minus 5. Oh, let's see. 4 squared is 16 times negative 2. That's negative 32. 13 times 4. That's, well, 10 times 4 is 40. 3 times 4 is 12. So 40 plus 12 is 52. Then we've got minus 5. And if you combine all those together, this is going to give us 15. Okay, so 4 comma 15. All right, last but not least, we've got negative 3. Okay, so negative 2 times negative 3 squared plus 13 times negative 3 minus 5. Negative 3 squared, that happens first, so that'll give us 9. So just looking here. Then we're going to multiply that by negative 2, and so that's negative 18. Let's see here, 13 times negative 3. 10 times negative 3 is negative 30. And then 3 times negative 3 is negative 9, and adding 30 and 9 together give us 39. Okay, so let's see, we've got negative 18 minus 39 minus 5, and that's negative 62. Okay, so here's our third coordinate. So here would be our points of intersection. Okay, so that's the end of section 1.2. Again, we'll be talking a whole lot about functions and their graphs and finding all sorts of things about them. This is just a really basic review. Please try some questions on your written homework. I believe questions, let's see. Definitely question 1. Yeah, question 1 you can work on. Actually, numbers 4, 5, 6, and 7 are also things that you can try, finding the x and y intercepts. Okay, so stay tuned for 1.3 coming up shortly, and I hope you have a great rest of your day.